Yeah. So I think we're going to go straight to the panel, and then all the questions will go there.
Sure.
So if you can stop your screen sharing. Yeah, thank you. Okay, so now we have our final panel of the day. Since logic languages are so good, why aren't they pervasive? So the Peter Stuckey, Bob Kowalski, and Daniel Heinz are automatically panel members, and David Warren will be chairing the panel.
Go at it.
I think most people can't understand recursion. Tragically, and if you can't understand recursion, then your declarative language is sunk, right? Doesn't matter what version, because we know, because we've spent a lot of time looking at this, that iteration is only recursion in a mathematical sense, but that leap just seems to be too far.
But Peter, but tail recursion is just a syntactic variant of a while loop, isn't it?
Absolutely. I'm with you. I mean, I think, you know, all of the like underlying mathematics of iteration is essentially recursion. Right?
Recursion. So we just have to not show it, right?
No. Recursion is incredibly powerful, and I have taught it to introductory programmers. It's not easy, and they don't all get it. And I mean, I agree with Peter that it's a real. It's just sad to me because it's such a powerful technique, and it's not that hard, but it is. I know, especially as Daniel said, that if you have a web programmer who's never taken a computer science course, you don't have a chance to get to them.
I think those guys are a lost cause, I think.
Well, okay.
Think of the next generation.
Before you rule them out as a lost cause, they're the ones doing most of the work on these systems that, you know, we use every day.
Well, they do web interfaces.
And I think also what happens is that most of the time, I think most programmers write a program by simply, I think, guessing the code and debugging through it. Logic program, the problem is that, you know, you write a program and you run it with great anticipation and the first answer is no. And you have no idea what went wrong.
No.
Oh, that's only if you're writing the program in Prolog, which most people don't do, as we've all agreed.
I think that the problem is not only recursion, it's also induction in mathematics. They don't understand this.
They're the same.
Sure.
No, it's worse. It's worse because that is, if you don't understand induction, you will never. I think induction comes before recursion.
Yeah, I agree.
Because
recursion. Agreed.
Baby, you see.
I think that the future belongs to the many cores. It's many cores on one chip. That is absolutely future. And we have fallen behind. We're not there, folks. And so other more kludgy solutions are being adopted, and they will win because they will have the performance and we will not, unless we step up our game somehow.
Is performance still a big problem?
Huge problem. For AI systems, it is one of the biggest problems.
Yeah, but most people just use off-the-shelf AI. They don't write.
Well, yeah, but AI is, in case you haven't noticed, AI is going into everything.
I would performance has been a big barrier in adopting Flamingo. It's you know, many orders of magnitude slower than the same logic programmed in JavaScript.
Python is an interpreted language, and it's extremely popular. And when they want to use TensorFlow, they use PyTorch, and they just link to C++ library. And anyway, performance these days, I mean, I think it's kind of a red herring, isn't it? I don't know.
It hasn't improved in a couple of decades on a per core basis.
Current Prolog systems are as fast or faster than JavaScript or Python. And it doesn't help or hurt. I mean, it just basically seems like people ignore it completely.
Well, there is a question.
Which really bugs me after all the work that went into that, right, Peter? I mean,
I would say that there is
Can I disagree at some point with almost everything everybody has said?
Sure.
Am I allowed to? Okay, first of all,
absolutely.
Yes.
Go ahead.
Okay. So first of all, I completely disagree about recursion because, like Leslie Lamport said, many programs are much more simply expressible, not by using iteration or recursion, but simply by using universal quantifiers. In the greatest common divisor example, the natural way for a human, never mind a mathematician or a computer scientist, the natural way for a human to express the greatest common divisor is along the lines that Leslie proposed, and it involves no recursion, it involves no iteration, because the iteration is supplied by the general cycle that Daniel, so basically my approach is very close to Daniel's approach. I was pleased to discover that a few minutes ago. So basically, you don't need to write recursions, you don't need to write iterations, if in fact the engine that you're running these things on supplies them for you, and all you have to do is supply the universal quantifier. Okay, if this doesn't make sense to you, then you really need to read the literature.
The
other, sorry, I think there's one more important thing to say. One more important, and then I'll shut up. The other important thing to say is that logic programming is really very inefficient because it uses frame axioms when it deals with reactive interaction with the world. Frame axioms are they're absolutely ridiculous. I mean, you need destructive updates. You need to destructively update either the real world, or you have to destructively update some model of the real world or some database, for example. You cannot use frame axioms. So basically, if I were to put my finger on why logic, forget about logic programming, why logic has made such a little impact in the practical world of computing, I would put my finger on the use of frame axioms, number one. And why logic programming has done so poorly is that it's focused on recursion, for example, and it's totally failed to appreciate the importance of reactive rules, the importance of condition action rules, because they look imperative. The actions look imperative, and because we haven't been able to devise the semantics for them. And I will shut up at this point. But let me just record. I disagree with almost everything that's been said up until this point.
For the whole workshop, or just the panel?
No, what's been said on the panel. I mean, recursion, efficiency, it's wrong to say that logic programs are efficient. It's wrong to say that people don't understand recursion. Those do not concord with my experience. I'm limited as it is.
I would agree with Bob.
I think Patrick wanted to say something. Let's try to get a little. Patrick?
If you compare with languages functional that have more or less the same problem, the fact that the OCaml is imperative, if you want, does not improve much the use of OCaml. I think if Prolog had imperative features, it will states and so on. It will not change the success. I think it's beyond. The success doesn't come from the language. It comes more for a community, hand-waving, social network. You see, some kind of fashion, or I don't know why, but I don't have the impression that Prolog is not a big success because it's based on logic. It's for some other reason, in my opinion.
No,
I don't know which reason.
But I can add some. Can I say something, David?
I was going to say, I think Paul had priority over the next one. Did you want to say something, Paul?
I would say that I basically agree with Bob's argument here that none of those language constraints are that critical. There are ways to encapsulate recursion, like in functional programming, you have the fold and other operations. And they actually isomorphic with what you would do in a procedural language. There is another thing that's very important. This is how I mimic Prolog in Python, and it's almost one-to-one. There are coroutine mechanisms like the yield operation in Python. With that, you can build generators, including infinite ones. And as soon as you push the language constructs to be comparable with what you have in logic, you actually steal from logic all the good things, and then you express them elsewhere.
Oh, I'm sorry. Okay, I'm supposed to call.
I think
I can only see certain people on my screen. It's only so many.
Carl has a question.
Carl.
Right. So I don't always agree with Bob, but in this case, I think he's put his finger on something. This update thing is absolutely critical. That you be able to have an implementation that really can change things, that like things inside itself. Now, where I potentially might disagree with Bob is I think that in these many core systems, this state change must be encapsulated inside actors that can protect the state change in a region of mutual exclusion. Otherwise, you have craziness of threads and locks and the other nonsense that you get with the other programming languages. So you have to encapsulate this state change, and then you can use the many cores.
Yeah, absolutely. I would agree.
One of the most loved.
Daniel.
One of the most loved programming languages, and one of the fastest growing right now. Everyone who uses it adores it. Is the Rust programming language, which uses linear types to make sure you don't have to manually manage memory while still being much faster than like a garbage collected language. So I think that I think what the insight there is that people wanted to be able to mutate the state freely, but they wanted a compiler to come and catch them when they mess up. So I think that there's a lot of potential in type theory to give us these kinds of things.
But so if I can make a comment, I think there are certainly niche areas where logic programming and answer set programming, and especially extended with constraints over real, can really have an impact. So one of the things that I'm working on right now is with people at Honeywell who want to model avionics systems and essentially make sure that they satisfy certain properties, they're safe and everything. And it turns out that event calculus is the best way to actually model them and ensure that they satisfy those properties, so that the semantic gap between the way they write those requirements for the systems and event calculus is nearly zero. And then with answer set programming extended with constraints, it actually works out very nicely. So there are these areas where logic programming can do really well.
I just want to say
Can I just quickly come in on the event?
I just want to say the obvious, which is that if different applications, different kinds of uses of computers can take advantage of our different languages apply for better at different applications. So if we're talking about reactive systems, and that's the only kind of program application we're talking about, then one set of arguments applies. If we're talking about other kinds, solving many problems that Mini-Zinc is very good for, which are very useful problems, then reactive system is probably not the way to go. Anyway, so Bob, sorry.
Well, the event calculus is all very well and good, having worked on it myself and followed the work as well. But the frame axiom is not good. The frame axiom doesn't work for large problems. The ontology of the event calculus is great. I mean, it is very similar to the action languages of Gelfand and Lifshitz, which Daniel's been working with. I was interested to see that he's following the lines that he is. But certainly on small examples, there's no question you can live with frame axioms with small examples, but not with realistic ones that drive people to imperative languages. And it's not just reactive systems alone. There are systems that combine both reactivity with deliberation, shall we say. You need both. One is not sufficient.
Yeah, so we're trying to work around the issues raised by the frame axioms, and so it does raise, causes problems, but so far we're able to overcome them. But maybe we can have an offline discussion on that.
Okay. Sure. I'd just like to point out transition logic was part of the inspiration behind our work, and it does use destructive updates, and it has a semantics which is, close to what we do, and is almost good enough for many of our applications. So there is work which has been done, which involves the use of recursion but not reactive rules. But transition logic goes halfway at least to meeting, some of my needs.
What I see as a big problem in general in the field is the pedagogy in the US and also in China. Insofar as people are exposed to logic as part of the undergrad computer science curriculum, it's classical, whereas there is the main successful logic in computer science, which is the logic of databases, which declarative logic programs and what most of the people in this conference work on is based on. And so I think to some extent the premise of the panel is somewhat misstated. It's why are we not able to get more recognition of the success of specifically logic programming in computer science?
Sure.
And I think that in UK and Germany and in some other countries, the undergrad syllabus does focus more in this area. But where would machine learning be if people hadn't learned calculus and statistics and linear algebra as part of their basic education? You would not have seen neural nets take off the way that they have. And the longer that I've worked in the field, the more that I see the fundamental lack of familiarity on the part of developers and also technical designers at the more junior and mid level career-wise is the #1 obstacle to adoption of practical logic programming systems. I mean, there are some things that we have going for us that are great, like explainability. And we can handle uncertainty. And we have compilers that are efficient. And yes, it's true that frame problem is somewhat of a sore spot, but actually there are a lot of techniques to address it. That's, I think, some of the latest advances do much better job, not just ALM, but for example, use of the undefined in Rulog and Floor 2 and now Sweet Prolog, as well as Coherent Knowledge's Ergo AI. They all can handle frame incredibly more efficiently than used to be the case. And that's the result of decades of work of people focusing on how to solve that problem. But so it is true that we can always find things to, improve. But I think the #1 obstacle, and we shouldn't take our eye off the ball, is that people don't connect the dots to realize that databases are logic, and they never learn about logic as undergrads in the 2 countries that are driving most of the practical commercial advance and the VC sector around it and the media around that relentlessly focuses on machine learning. Sure. Partly because of that. They don't even know how to talk about semantics, literally.
Just okay, Patrick.
Oh, no, go.
Peter?
I'm looking forward to this decade because machine learning is going to hit combinatorics and they're going to fall over big time. There's millions of papers on machine learning approaches to traveling salesmen. And, they can, after 10,000 training hours, find good solutions in almost the same time it takes Concur to prove optimality, right? And this is where they can make training data, because you can make arbitrary amounts of training data for a TSP. But in the real world, if I go to a commercial client, if they give me 5 examples of their problem, I'd be so happy. So, big data or machine learning, and at least in my space, in discrete optimization, I'm looking forward to it hitting the iceberg and discovering that there's a lot more under the surface than they know about.
Peter, I think Peter had a question.
So I just want to kind of summarize what many people have said. So I think logic has found its place. But the world is multi-paradigm, and you need to the concepts for the problem you're solving, and logic is not the right base material for everything, of course not, but the use of logic is very important in databases, like Benjamin was saying. It's actually, the relational model is a data log, so that's a big success. Constraints and operational research where the constraints are the glue is a big success. I think also there are some hidden under the radar successes in distributed systems. There's a concept called CRDT, conflict-free replicated data types, which achieve consistency without consensus. I think Leslie Lamport invented Paxos, which was considered the keystone of distributed systems, the consensus algorithm, for many years. But I think nowadays it is actually still important, but there are many other things that are taking its place. In a CRDT, you can have consistency without consensus, and because it is monotonic, because it is defined using joint semilattices, and you can use it, so it's very close to logic, in fact. And so the notion of declarativeness in general, I think is actually coming up very strong. Also, functional programs, most cloud analytics tools are actually declarative, starting from MapReduce. They're functional, and the reason is very simple. A large distributed system can only be made fault tolerant in a simple way if it is functional. So MapReduce is functional for a good reason, okay? And updating that with single assignment variables and so on, it's very close to logic. Many of those systems are also forms of logic. So most cloud analytics tools are functional logic, even though it's not advertised very strongly. That's all.
Okay, Carl had one comment he wanted to make, and then I want to call on Dave Meyer.
Yeah. Let's see. Am I unmuted? Yes. Okay. So I think, for better or for worse, Peter, I don't think we can rely on these stimulus response networks falling over, right? They are going to take over and provide the basis for universal surveillance of all. They have a big future ahead of them. And the Chinese are mastering this, in Xinhua in particular, but other places in the country. So we're going to see even more massive surveillance based on these stimulus response networks. And Facebook and Google and other companies, the US champions, are going to make even more money in terms of doing their surveillance for political and economic purposes. So they have a bright future ahead of them.
Sure.
I think the only thing we can do is to incorporate these little recognizers into our larger architecture. And that's the way to go. And I think that Peter and other people have previously agreed with that. We cannot count on them falling over. They will become much more successful. And we need to make use of that technology in our logic systems.
Yeah. Okay.
Okay, thank you. The reason I was going to call on Dave is because I saw a thing in the chat that Carl mentioned, claiming that the one claim was that SQL is the most popular declarative language and the most used.
I didn't say it was declarative. It is a logic language, but not pure.
There we go. Okay, now I want to ask Dave about. That's why I wanted to call. I wanted to set up that Dave could say something. By the way,
purity is not important.
Peter, shut up.
Paradigm. Okay.
Dave, you're on.
I characterize SQL more as the most successful domain-specific language, and I think that's something that is kind of what I've heard coming and going through in talks throughout the day, is that having a model of the domain, having your verbs and nouns correspond to that domain, having something like an intermediate algebraic representation that you can prove things about or manipulate, I think is where the power comes from. And so, I've seen a lot of things where that intermediate form is logic language. But to me, to point at SQL is the fact that it was, it's domain specific. It helps you do a certain class of things. And, I am not going to write an efficient matrix. Well, no, there are efficient matrix multiplies. You know, I'm not going to try to do necessarily, you know, n-body problems using my SQL optimizer.
Okay. Okay, we're at the end of the time.
Costis wanted to say something.
Yeah, I had a question I had actually two questions, one for Peter, one for. So let me say the one for Peter first. So I was a bit. Now I understand, of course, that Minisync is not a language that has been developed as a programming language. The aim is different, but I was a bit shocked by going down in the expressiveness, and then rather, at least from the mortgage example, of course, this is just an example. Yeah. Then so is there something to learn there from?
So one thing to learn is, I mean, the main jump was essentially removing recursion and replacing with iteration, right? So maybe that's where my intuition comes from, what's difficult about programming languages. But it's also that basically for discrete optimization problems, the hard part, the hard part is solving them. So what I want is a language to express the constraints, which I don't need a full programming language to do, essentially, right? The interesting thing is that, of course, and this is where we sort of recreate it, is because then we don't actually just want to express constraints. Once we start doing incremental solving or more complicated things, we end up needing to bring back the tools that we used to have. Interestingly, though, I sort of swept this under the carpet. We're not going back to exactly CLP because the search heuristic will probably be written in some imperative language. So I'll avoid the frame update problems by doing that loop in imperative style, right? Because it turns out that's typically what I want for this complicated discrete optimization algorithms. I want to understand some previous state. I want to keep track of things like that. So I'm not sort of saying we're going back to CLP, but a lot of the features that were in CLP already, which we could already do, we lost, right? And we did that for a reason because, well, now our solving technology is like jumped ahead, way further ahead, because actually it's much easier to solve a problem if you're giving me a fixed set of constraints to begin with and nothing else. So there was a purpose to shrinking the language to make the kind of underlying, the hard part of the problem a bit simpler because we only have to solve a problem once. And then sort of leaving the stuff outside. In some sense, it's another example of multi-paradigm. I hope that answers the question.
Yeah. So my second question was for Bob. It's a bit of a personal question since I have a daughter that is quite young. What are your experiences from teaching logic to children? You mentioned this at some point, but then you connected it to the Japanese 5th generation. It wasn't clear.
Well, there was an issue to do with the difference between the procedural and the declarative interpretation of our logic programs, and at that time we didn't have tabling, so when we wrote nice programs, they would sometimes go off into a loop, and the teachers didn't know what to do or what to say, and that caused tremendous havoc. With tabling, I think the situation totally changes. Also, there are people teaching ASP now in schools to high school students, and that's very promising, although I would suggest that they should teach Peng, the natural language English version of ASP, rather than the symbolic version that makes it so much harder for children. Anyway, very quickly, let me say that children should be taught English. They should be taught that English is meaningful. They should be taught that you can use English precisely. When Annie summarized Lamport's greatest common divisor algorithm, she used English, and it was very close to an executable representation. And if children were taught to use English precisely, it would be computable. and they wouldn't need to use symbolic representations.
I have a question to Bob too, if I may. Bob, I was wondering about your criticism of frame axioms. Take, for instance, this old work that Michael Gelfand and his students did 20 years ago on encoding the reaction control system of the space shuttle. It encoded solved the frame problem for that rather complicated domain using logic programs with negation as failure. So what do you think is wrong with efforts like this?
Well, for small databases, for small states, then you can afford to reason to duplicate. So basically what the frame axiom does is every time you update a state is you look at every fact that doesn't change and you reason explicitly that it doesn't change. Either you do this in the forward direction or the backward direction. And that's you may not even notice it for small databases, but for any database or any memory, variables with memories that, in conventional programming languages that just wouldn't work, it would just fall apart. So the AI community has so distanced itself from the programming and database communities that they don't seem to have any instincts about the inefficiencies of the frame axiom, because they deal with, well, we deal with typically small baby problems.
It seems to me that say this example of this reaction control system, there was a rather complicated system where effects of actions were often indirect. I mean, you push a button and then it causes some liquid to go from one part of the domain of the shuttle to another, and so on. So there was no need to mention individual actions and their complicated effects. There was just standard formalization of the common sense law of inertia, saying values of fluence remain the same in the absence of information to the contrary. And that seems to be a very compact form which solves the frame problem. You don't have to modify it as you include more actions or more remote indirect effects.
Oh yeah, the frame problem is solved by exactly what you say. I mean, and we have that in the event calculus that was there in the situation calculus. But if you have many fluents or many facts, you just can't afford to do that reasoning. It just, nobody uses that. There exists no programming language which is imperative based on algorithms viewed as state transitions. There's no programming language that reasons with frame axioms, and for very good reason. It's like the world. The world doesn't work with frame axioms. The world doesn't exist in all of its states simultaneously. The world changes destructively from one state to the next.
So do I understand correctly that what you're saying is that we can probably write for such complicated domains a compact declarative representation, but when you want to do query evaluation, when you want to really execute your programs, then it becomes problematic when the domain is complex. Is that what you're saying, or do you?
Okay. Let me take an analogy. Suppose you write a program for adding two numbers, a recursive program for adding two numbers. One of the properties of that would be that addition is associative. Now, what we do with frame axioms is we take, in effect, the associativity axiom and reason with it explicitly. It's a true property, which is wonderful, but we don't have to use it for reasoning about how to add 2 plus 2. We don't want to, or 2 plus 3, we don't want to reason with using the associativity axiom. We want the associativity axiom to be a true property, but we shouldn't be confused about using it to reason. So there are some properties which are explicit and other properties which are implicit. The frame axiom should be an implicit property. It should not be used explicitly.
Maybe it feels this is all interesting, but it seems to be we're getting into the weeds, seeing as how we're 10 minutes over the end, past the end of the workshop, which is.
Actually, I have some questions, but I think maybe what we can do is we just leave this open. People can chat a little bit, and maybe David should just close it officially for your thoughts. And
okay.
if you're more relaxed too.
The panel, and I guess the work.